I'm very happy to have with us now Jörg Althaus, who's the Global Segment Coordinator PV Power Plants at TÜV Rheinland. Jörg is also a true solar pioneer, so he's in solar for over 20 years. He's also with TÜV Rheinland for over 20 years and always dedicated in improving the quality of solar power system, because that's what TÜV Rheinland stands for. So I'm really happy to have Jörg with us today to talk about the quality aspects of very high power modules, because as we know, once new technologies come into the market, they also have to overcome some challenges with materials, with design, and many other factors. Jörg, we're looking very much forward to your presentation.
Thank you, Michael. I thought you were going to say solar nerd there, but okay. Let me just share my screen. Yeah, somebody has to make me host, please. Okay, you can see the screen?
We can see you, but not your presentation.
Okay. It should be working now. Okay.
Yeah.
All right. Thanks for the introduction, Michael, and hello everybody from my side, from beautiful Cologne. You see the rooftop here with filled with solar. I was approached by Michael to give some insight on the quality aspects of the, as TaiyangNews calls them, very high power modules. So let me just get started, just starting with a little refresher of where we come from, but some of that is already mentioned by Dr. Drobe. Influencing factors for high power modules and some national requirements and conclusions. So I stole here a figure from the Jet Propulsion Laboratory, quite old one. So you just see what the modules were when we look back in the 70s, very early on. Not so interesting now, of course, but just as a reminder, started very small. And then we took some data, which you've seen in different formats just before. Module length and width is the blue and green on the left, and then the module area with the yellow line over the years. As what you can see here, basically, that is also from the experience that when I started, basically modules stayed the same size for a very long period, no change. And then in the recent years, the increases came. Of course, that's not quite fair to state it like this, because that's only true for crystalline modules. The thin film modules actually, I think it was 2017 or 2007 or 9, I think, when the Gen 8.5 were introduced by Applied Materials, which were actually 2.2 meters by 2.6 meters at the time. And they were supposed to go all in big area ground-mounted PV power plants. A great concept at the time. It didn't turn out with the efficiencies. But so the concept of very big modules is not totally new. But of course, the crystalline technology has had a kind of a bit different history. And just recently, there was a presentation by NREL that looks also a little bit in the future. I think there were some questions in the chat also, what's coming. So basically, we are here now at 2020. It's the same what you've seen on the other slide, just visualized different. And then what's coming is, now we're cutting mainly modules in cells in half, more cuts, and then the modules might get slightly bigger again. But NREL foresees with new technologies, with tandem and so on, to more or less stay at the same size, but going up to 1,000, 2,000 watt even per module. So maybe that's answering some of the questions in the chat, but of course that's a prediction which nobody knows the certainty about in this this industry. Now, what I would like to go into is from the life cycle of the PV module or the PV technology to have an insight on some of the influences of the large modules or high power modules that I see or we see. So, of course, you have the module design, you have some component design, you might have some reliability topics and process. And I will only go into those in the red because time is limited. But of course, we heard about packaging and container sizes and how the logistics might be affected. And then, of course, you had TaiyangNews had a presentation on trackers not too long ago, where also the large modules were discussed at length. So first, coming from the standards, main dominating standards for approving PV modules globally are the IEC 61215 and 61730. And there is also a document that requests what a PV module manufacturer has to do when he changes something on the product for requalification. And there are clearly some things that are to be done if modules get larger or current is increased or power is increased and so on. So just a snapshot here saying what kind of tests from these standards are relevant for what kind of change. Not going to go into depth, it's just mainly saying, okay, for module size change, quite a few of the reliability qualification tests have to be done. And then, of course, if you change the ISC or VOC, you might also have some issues with bypass diodes and hotspot occurrence and so on, but I'll go into that. More modules, the larger modules, likely also with the cut cells, come into having, with a larger wafer size, more cells per string, which would increase the module's performance parameters, which is, of course, what we're all looking for. That in mind, though, however, with cells getting bigger, but trying to optimize the module area, typically what is happening is people are trying to minimize the distances between the cells and also minimizing the distances towards the frame and so on. And the small distances, however, have the potential, at least, to cause higher thermo-mechanical stresses on the wafers or cells. So with these new concepts, any new technology also brings along opportunities, but also risks that have to be studied and checked for the best embedding materials and so on to cover for those additional thermomechanical stresses. When we have higher string power, potentially use more cells per bypass diode, we also have higher reverse currents in the module, and then if the hotspot protection scenario or concept with diodes is not sufficient, then we will see local overheating of cells, which we would call a hotspot and might cause delamination or even charring or burning. So these are risks that are totally known in the PV industry, well understood, but of course, with currents now exceeding well beyond 10, 20 amps, the risk are potentially higher and need to be taken care of. From the mechanical stress, you see here, of course, a static mechanical load test. There's also dynamic testing and inclined mechanical testing. However, with the modules getting larger, potentially frames also need to be tougher because the mechanical stress is just bigger on the if it's a 4-clamped module, the stress on the clamps is bigger, and ultimately on the frame, you can see here one of the larger modules with a bent frame. Something not necessarily related to size, but to bifacial, and also probably been discussed in previous sessions. Then, of course, if you have frame or bypass diodes partially shading cells, you get some current mismatch, or can have some current mismatch on the module rear side performance, and that would be seen in the IV curve as a dent which needs to be just interpreted correctly or try to avoid by designing the electric connection and framing differently. That's a few excursion on the module design, but on the component design, it continues, of course, with the higher currents. The stress on each component is also increased. That means, of course, we need to choose the components wisely. Are the connectors and cables suitable for the higher currents? But also the size of the junction box with the heat coming from the bypass diodes might need to be adjusted, because there is more power, also more thermal power, and hence we need to make sure that the temperature can be carried out of the source. If we look at the reverse behavior of a module, in case of some failure, it can happen in a PV system that single modules or multiple modules are running in reverse, and you can see by an infrared image then what kind of heating you might expect, because of you're testing at 1.35 times the short circuit current, the string current, and therefore you can achieve quite high currents and high power. And here you see that this particular case, 92 degrees were achieved, which is quite high for some of the polymeric materials. But of course, it's also very high for the diodes. Looking into that on the next slide here, higher short circuit current also results in higher potential reverse currents, which would then result in higher diode temperatures and leakage currents. So the question we have to ask ourselves, is the diode that we select fit for the use, or will it overheat? No rocket science again here. Of course, you can choose the right diodes, but it's not just taking your natural module design, making it a little bit bigger and everything is fine. It needs to be redesigned properly. Going into a little bit of the reliability, just an excursion because we don't really have the time on that. Just giving you an update, you might know that the IEC 61215 was recently published in a new edition, also considering bifacial performance measurements, and also just last month the IEC TS 63126 was released, which is a standard that looks particularly in harsh environment performance. And as a lot of these large modules are ending up in ground-mounted PV systems in arid or hot climate areas, then of course it's also important to see if they would withstand that. The picture on the right is not very relevant for a large area, 800 watt modules or something, because they most likely wouldn't end up on the roof. But the snow still is a topic for, at least in our, where I am in Cologne, Germany, also for ground-mounted systems, and therefore non-uniform snow loads are something that, of course, bigger modules would also have higher impact under. So much about the module and component design. The next thing is kind of related also, because when you see the large gigawatt factories, then of course they've been built over the last years, and also have their inline and sometimes R&D laboratory facilities, but inline power measurement flashers. And those flashers have a certain light uniformity. You would see here in this image, you know, seen by darker areas being having less light, and brighter areas are the areas with uniform light. And usually the module should sit right into this image of the bulb of the flasher and see uniform light. Now, if you use the same flasher and put a larger module in, you might end up having cells on the edge of the module seeing less light than the cells in the middle of the module. Which would then mean that the solar simulator does not reach its classification anymore. Classification means the uniformity, the spectral response, and temporal stability gets classified by a standard 60904. And if the uniformity is not sufficient, it will have an impact on the measurement uncertainty, seeing also some bends in the curves and so on. So that's not only true for laboratories, but of course for all inline measurements where the power rating would be done. Giving you here an example, I borrowed from Eternal Sun's Bayer, their previous version, inline flasher, which has the module laying sunny side down and the light is coming from underneath. Usually this sort of simulator is used for inline because the modules can be moved over it, while some factories might also use tunnel designs where the lamp is at a distance. For both designs, what I said before is relevant. Here you just see there's a new product on the market. On the other hand, if you use tunnel simulators, then of course you have the opportunity to move the lamp further away, but you might have to compensate by running at higher power, which would reduce the light source's lifetime. For other equipments also, predominantly in reliability testing, also for manufacturers in their own facilities, some might run into capacity issues. UV chambers is something that is, with the new standards, also a bottleneck for some laboratories. With the modules getting larger, that might even increase. Same goes for light soaking, for LETID, for light-induced degradation testing, and so on. Mechanical load tester, some of the designs available, they would not fit the newer modules. One thing not necessarily in everybody's mind is the environmental chamber testing. Usually has the modules run under electronic load, so there's a current flow going through them, and a lot of the electronic loads were limited to 200-300 watts, and so very large modules might need additional designs. Reverse current, same for the power source. Wet leakage basin, you see here image very large basin, but some basins are quite small. So we were kind of lucky that we designed our laboratory when the thin film modules were very large in 2007-09, but I've seen a lot of other laboratories that I know would run into capacity issues now. Another thing is for building integration. I know that these very large modules, most of them likely will not end up on residential roofs, but maybe on commercial roofs. Some of the ground-mounted facilities also are classed as publicly visitable. So in that sense, they might fall under the construction products regulation. And this is national-wide for Europe. It's each nation or each country has its own requirements. And I know for Germany, for example, if you go on residential roofs or you have any sort of building like a carport, also belongs to that. There's currently a limit of 2 square meters of module size before you would require a national technical approval, which requires additional testing, additional authorities to be involved. That's for Germany, but I know also some other countries that have additional sort of regulations in place. So that needs to be kept in mind. To conclude, I would say PV module sizes have substantially increased in the recent years. Each new technology brings with it also potential new risks that need to be studied and also look at the potential impacts. Must say in our laboratory we've tested some of these new designs. I cannot now say there are considerably higher failure rates or something, but it's also only the beginning of the technology. So we have to check if the standards are still good enough for all of it and so on. So more test experience is required to prove the quality and long-term reliability. When designing a module, the components need to be chosen wisely and fit for the specification stresses. For particularly the stress tests that simulate thermo-mechanical fatigue are, in our experience, in the first experience, quite critical. Test equipment might require upgrade. that's also something that a buyer should look into when inspecting a factory that he's buying from. Are, for example, the flashers suitable for the larger modules? And as I just mentioned, for BIPV, additional requirements might be in place. With that, I conclude my presentation, and I also would like to invite you to our snack booth at E1006. You can see here a couple of webinars coming up, but I don't have the dates yet. We will see on social media. With that, I would be open for some questions, or if you allow, Michael.
Yes, you're good in time, Jörg. Thanks. Maybe I think so. There was one question actually also from someone asking about warranty terms. You know, I think Jutta also mentioned that, but of course you're also seeing that. So we have now 25, glass is 30. That's the standard, and so and Jutta kind of said 30 probably will be the new normal then for glass, but can we have 35 years of warranty, performance warranties given or not? Because there's of course a risk assessment involved from the company, and it's about insurances, and it's all these discussions which a company has to take into consideration when they do that. But if you look at testing from the testing side at the modules, how long do you think they can last? Also, when we're seeing now this change to boron doping, fewer degradation, and such things.
Yeah, Michael, I mean, it's a question, of course, that is frequently asked, and with the reliability testing getting more mature, I think we can be confident that there will be sufficient foundation to make 30-year or even higher predictions of warranty. However, stating that we're looking into the future, and we have also seen there, we're looking at perovskite and tandem technology. Also for those, I think once they come to the market, they will be early in the market, and the long time experience is not there. So I'm kind of hesitant to say, and also what VDME said, that okay, we will go down with the initial degradation from 2% to 1%. I'm not sure if we're there in 5 years with new technologies. Maybe we're back to 2% to start with, but from the reliability and long-term warranties, I'm quite confident that the 30 years can be achieved, because we will come up with better test scenarios.
Okay, you've shown actually at the moment these big laminators for up to 2.54 meter modules. Actually, I think Jutta showed that we're seeing also 3 meter plus modules that will come. So that means so how much issues do you see for test equipment there? And then also the other question would be, what do you think is the maximum weight for a module? Not only size but also weight, even if it is a utility scale product.
Right. I mean, I mentioned it briefly when we look at, I think it was 2009, that the Applied Materials back then came out with the Gen 8.5 glass thin film amorphous silicon technology on long bars, pre-assembled, and they were 2.20 meters by 2.60 meters, so more than 5 square meters, and they were just offloaded from the trucks in the site directly on the mounting dishes. That was all thought through. It's just that they just didn't make it from the production cost and also the efficiency requirements, I think. But for this, I mean, we designed our lab back then for these size of modules. For up then, I don't see a big issue. The image I showed was a flasher, not a laminator, but of course, since the thin film modules also got laminated, the laminators were also available for that size of module. That's not the main issue. I think for the size of handling, it probably will not go much beyond that, because then you don't get advantages from the shipping and the local transportation. Also, these large modules that were quite heavy glass, some of the power plants I've seen, you wouldn't be able to run a truck through like that with that weight on it. So it becomes more or less a question of on-site logistics, what makes sense. And I think that, you know, I don't see it going much bigger than that, unless everything is going to be done by robots in the future. You know, I don't know. I cannot hear you anymore.
I heard that I have an echo, and that's why I muted myself when I'm not talking. So, but I think there's no question directly now, but if you could stay for a little while, if you have some time, that would be nice, and answer some questions in the chat, that would be great. Yeah. Okay, thanks Jörg for this great insights.